Hi, and welcome back to Tactical DevOps. I'm Joe.
And I'm Jane. Today we are taking a look at cluster architecture and installation.
Yeah, and to really set the stage for you, the listener, I want you to just imagine for a second that you're running this massive, truly global e-commerce platform.
Right. Oh, like the classic Black Friday scenario.
Exactly. It's 3 o'clock in the morning on Black Friday. Your traffic is just, spiking to like 100 times your normal baseline.
Sounds terrifying.
It is. And then suddenly a power surge takes out an entire rack of servers in your primary data center. In a traditional setup, alarms are screaming, right? Pagers are going off.
Yeah, people are waking up in a panic.
Right. Your site is down.
Yeah.
You are losing tens of thousands of dollars every single minute while human engineers frantically try to manually spin up replacement servers.
Which takes forever.
Exactly. But in a modern Kubernetes environment, the system basically barely blinks.
It really doesn't.
Right. Within milliseconds, this invisible control mechanism detects the failure, calculates the lost compute capacity, and just, seamlessly spins up identical replicas of your apps on healthy servers.
Yeah, your customers never even notice the outage.
So welcome to another deep dive. Today, we are tearing apart the machinery that makes that exact scenario possible.
We really are. We're demystifying the architecture, the installation from bare metal, and the security configuration of a cluster.
It's the ultimate invisible safety net.
It is, but, getting to that level of automation requires a really profound understanding of how all these underlying components interact.
For sure.
We aren't just looking at, like, a piece of software today. We're analyzing this highly distributed self-healing organism.
Yeah, and for those of you looking at the certification tracks, understanding this architecture and how to build it from nothing, well, it makes up a massive 25% of the core knowledge domain.
That's a huge chunk.
It is. But we're not going to just, sit here and memorize a list of tools or flags. We're going to deconstruct the mechanical reality of how these systems talk to each other.
Yeah, how they isolate processes and how they maintain a single source of truth when physical hardware is just, constantly failing.
Right, because hardware always fails eventually. Okay, let's unpack this. Our sources give us this really dense blueprint, starting right at the top with the central nervous system.
The control plane.
The control plane, exactly. Now, the text lists 5 distinct components running here. You've got the Kube API server, etcd, the Kube scheduler, the Kube controller manager, and the cloud controller manager.
That's the core team right there.
Right. And I want to start with the Kube API server because the documentation calls it the front end for the Kubernetes control plane.
Yeah, it's the receptionist.
Right. But wait. If every single request, whether I'm typing on my laptop or it's just a background process, if it all has to go through this one single API server, doesn't that create a massive bottleneck?
You'd think so, right?
If I am spinning up 10,000 pods in a minute, how does a single entry point not just instantly crash under that load?
That is exactly the right question to ask. It really gets to the heart of distributed system design. The Kube API server is the single gatekeeper, yes, but it is entirely stateless.
Oh, stateless, meaning it doesn't remember anything.
Exactly. It does not store any information locally on its own disk. Because it's stateless, you don't just run one Kube API server.
Right, you'd run a bunch of them.
Yeah, you run 3 or 5 or 50 of them, all sitting behind a network load balancer.
Ah, okay, so it spreads the load.
Precisely. When your 10,000 requests hit the cluster, the load balancer just distributes them seamlessly across all those active Kube API servers.
Okay, that makes sense.
They're in there processing thousands of REST API calls, validating cryptographic signatures, checking your authorization.
I do all the heavy lifting.
Right, checking your RBAC policies, mutating the requests if they have to. But the Kube API server itself has no memory. It just processes the logic.
So it's essentially a massive array of, highly trained receptionists, all strictly enforcing the building's security policies.
That's a perfect way to look at it.
But if they don't have any memory, where are they writing down these requests? Because if I tell the cluster, hey, I want 5 Nginx web servers, it has to remember that fact.
Right, it can't just forget.
Yeah, even if the specific Kube API server that took my request gets rebooted, the cluster needs to know I still want those Nginx servers.
And that brings us to the second component, which is the true brain of the operation, etcd.
etcd, right.
The source text explicitly defines etcd as a consistent and highly available key value store. This is the only stateful component in the entire control plane.
The only one. Wow.
Yeah. When the Kube API server processes your request for 5 Nginx servers, It translates that into a specific key-value pair and writes it directly into etcd.
But etcd isn't just like a standard SQL database, is it?
No, not at all. It is a distributed cluster database,
Yeah.
and it's built on something called the Raft consensus algorithm.
Raft consensus. Okay, I've seen that term thrown around, but it always feels a bit, I don't know, opaque.
It can be, yeah.
I mean, you know what a database is, but why does Kubernetes require this specific, highly complex algorithm just to store key value pairs?
Right.
Like, what happens if it just used a normal database replication setup?
If you use standard asynchronous database replication, you open yourself up to a really dangerous situation called a split brain scenario.
Split brain? That sounds bad.
It is bad. Imagine you have a network partition. Say a physical cable gets cut somewhere in your data center, and your cluster splits in half.
Okay, so the two halves can't talk to each other.
Exactly. The left half of your cluster thinks you want 5 web servers, but the right half hasn't received the latest update, so it thinks you only want 2.
Oh, I see.
So they both start trying to enforce their own reality. Chaos ensues. You get duplicate pods, IP conflicts. It's a mess.
Total nightmare.
Yeah. So the Raft consensus algorithm prevents this through strict leader election and quorum.
Okay, break that down for me. Leader election.
In an etcd cluster, which is typically made up of 3 or 5 nodes, there is only ever one leader.
Just one.
Just one. The other nodes are followers. When the Kube API server writes data, it always writes to the leader.
And the leader doesn't just, say, okay, I got it, and move on, right? It has to make sure the followers agree.
Precisely. The leader sends that write request out to all the followers. And the write is only considered successful, meaning it's actually committed to the database, when a strict majority of the nodes acknowledge they received it.
So that majority is the quorum.
Exactly. If you have 5 etcd nodes, you need 3 to agree.
So what happens if that network cable gets cut again?
Well, if the leader is suddenly isolated with only one follower on its side of the cut, it can no longer achieve a quorum of 3.
Right, because it only has 2 total nodes on its side.
Right, so it immediately steps down, it stops being the leader, and that side of the database stops accepting writes entirely.
Wow. So it just shuts down its ability to change.
It chooses to freeze and protect data integrity rather than risk a split brain scenario.
That is fascinating. So when the text uses the word consistent, it means that no matter which node you read from, you are guaranteed to get the latest quorum-approved truth.
Exactly. There's no guessing.
And highly available means you can literally take a sledgehammer to 2 of your 5 etcd servers, and the cluster just keeps on humming because the remaining 3 still form a quorum.
Yep, it's a completely bulletproof vault.
It's a bulletproof vault. Okay, so the Kube API server takes the order, and the Raft algorithm locks it into the etcd vault. But neither of those components actually does anything to, spin up the web server.
Right, they don't touch the compute resources at all.
They just record the desire.
Yes, they simply establish the desired state. Moving from desired state to actual state requires active participants. And that brings us to the Kube scheduler.
The dispatcher.
Exactly. The source document says the scheduler watches for newly created pods and assigns nodes.
I really want to focus on that word watches, because in standard programming, you usually write a script that says, do A, then do B.
Right, imperative programming.
Yeah, it's imperative. But Kubernetes is declarative. The scheduler isn't being explicitly told to do anything. It's just sitting there monitoring the etcd database through the Kube API server.
Yes, and it does this through incredibly efficient gRPC watch streams.
Just constantly listening.
Constantly listening for a very specific event. A pod object that has been written to the database but has a blank field where the node name should be.
Ah, the node name is blank.
Right. That blank field is basically the scheduler's bat signal. It says, hey, we have a cargo container, but it isn't assigned to a delivery truck yet.
But the scheduler doesn't just pick a node at random, right? I know there's a massive amount of algorithmic filtering happening here. How does it actually decide where this workload goes without just overloading the closest server?
It is a rigorous 2-step process, filtering and scoring.
Okay, so step 1, filtering.
First, the scheduler looks at the pod's requirements. Does this pod require 10 gigabytes of RAM? Does it need a GPU? Does it have a rule that says it must run on a server labeled as US East?
It checks all the constraints.
Right. The scheduler runs these predicates against every single node in the cluster. It filters out all the nodes that physically cannot run the workload.
So if you start with 100 nodes, this filtering step might eliminate, say, 80 of them.
Easily, yeah. leaving you with 20 capable nodes.
But you still only need one.
Exactly. So step 2 is scoring. The scheduler runs a series of priority functions on those remaining 20 nodes.
Priority functions, like what?
Like, which node has the most available memory right now? Which node already has the underlying container image downloaded, so it'd start faster?
Oh, that's smart.
Or which node would result in the most balanced spread of workloads across your physical server racks so a power outage doesn't take down the whole app?
So it calculates a mathematical score for each node, ranks them, picks the winner.
And then, this is crucial, it does not start the container.
Wait, it doesn't?
No, it simply goes back to the Kube API server and updates that blank node name field with the winning node's name. It just updates the database.
That's wild. It's all just data manipulation at headquarters. The scheduler just updates the record and walks away.
Yep.
Okay, that leads us directly to the fourth component, the Kube Controller Manager. The source vaguely says this runs controller processes, but if the scheduler is doing the dispatching, what exactly are these controllers doing?
What's fascinating here is the concept of the continuous control loop.
The control loop.
A controller is a highly specialized piece of software, and its entire existence is dedicated to a single, relentless mathematical equation. Actual state minus desired state.
Actual minus desired.
Again, there isn't just one controller. The Kube Controller Manager is a single binary that bundles dozens of distinct controllers together.
Dozens of them?
Yeah, you have the replica set controller, the node controller, the endpoint controller.
Let's make that concrete for you listening. Let's look at the replica set controller. We put 5 Nginx servers into our desired state, right?
Right. The replica set controller is constantly watching the Kube API server. It asks, how many Nginx pods are supposed to exist?
The answer is 5.
Then it asks how many Nginx pods actually exist in the cluster right now. Let's say one of your physical servers suddenly lost power, taking 2 pods down with it.
So the actual state is now 3, but the desired state is 5.
The controller immediately detects that delta. And notice, it doesn't try to fix the broken server.
It just abandons it.
It simply generates 2 brand new pod definitions and hands them to the Kube API server.
Which then triggers the scheduler to assign them to new nodes, completely closing the cycle.
Yes. It's an autonomous, self-healing loop.
It acts exactly like a complex industrial thermostat. Like, it doesn't just turn the heat on and walk away. It constantly monitors the ambient room temperature, firing the furnace anytime there's a slight drop, and shutting it off the exact millisecond the desired temperature is reached.
That is a perfect mechanical analogy. The control loop is edge-triggered, meaning it reacts instantly to events, but it's also level-driven, meaning if it misses an event somehow, it will eventually catch up on its next routine scan of the database.
It's incredibly robust.
Very. And the final piece of the control plane is the Cloud Controller Manager. The document notes it embeds cloud-specific control logic.
I've always found this component interesting, honestly, because for years, Kubernetes had all the code for AWS, Google Cloud, and Azure baked directly into the core source code.
Oh, it was a monolithic nightmare.
Just massive, right?
Yeah, every time a cloud provider wanted to update their specific load balancer logic, they had to wait for a massive global Kubernetes release cycle.
So the Cloud Controller Manager decoupled that.
Exactly. The out-of-tree architecture solved this. It decoupled the core Kubernetes logic from the proprietary cloud APIs.
So if a controller notices that an application requires a public-facing IP address, it just passes that request to the Cloud Controller Manager.
And this component knows exactly how to make the proprietary API calls to AWS to provision an elastic load balancer, or to Azure to set up their networking appliances. It acts as the universal translator between open source intent and proprietary infrastructure.
Got it. So to synthesize this entire control plane for you, Kube API Server is our stateless, highly scaled gateway. etcd is our bulletproof RAF consensus vault.
Right.
The Kube Scheduler is our mathematical dispatcher running filtering and scoring algorithms. The Kube Controller Manager is our array of relentless, self-healing thermostats. And the Cloud Controller Manager is our external liaison.
That's the headquarters.
But here's the stark reality. You could have the most perfectly configured control plane in the world, and it will do absolutely nothing if you don't have the compute power to actually execute the workloads.
Headquarters is nothing without the workers in the trenches.
Exactly. And that transition from the abstract, declarative logic of the control plane to the physical reality of CPU cycles and memory allocation brings us to section 2.
The node components.
The node components. This is where the actual code of your applications executes. Our source outlines 3 key components running out there in the field. The kubelet, the container runtime, and the kube proxy.
Let's start with the ultimate worker bee, the kubelet.
The text describes it as the agent that runs on each node. Now, when I hear the word agent, I immediately think of a mindless drone just, waiting for commands from the mothership.
Sure, that's a common assumption.
But based on our discussion, the kubelet has to be vastly more sophisticated than that, right?
Oh, absolutely. If we connect this to the bigger picture, the kubelet is the ultimate localized foreman. It is highly autonomous within the boundaries of its specific physical machine.
Okay, so it has agency.
Yes. Remember how the scheduler updated the database, putting the name Node 3 on our pod?
Right, the blank field got filled.
The kubelet running on Node 3 is continuously polling the Q API server, asking, hey, is there anything assigned to me?
Just checking its inbox.
Exactly. And the millisecond it sees that pod, it pulls down the specification. But the kubelet doesn't just blindly run the code. It has to physically prepare the operating system.
Here's where it gets really interesting. Because when we say run a container, what we actually mean is partitioning a Linux kernel.
Yes.
The kubelet has to carve out dedicated resources.
Exactly. The kubelet interacts deeply with the Linux kernel using two fundamental primitives, C groups and namespaces.
C groups, control groups.
Right. If your pod spec says this container is only allowed to use 500 megabytes of RAM, the kubelet doesn't just politely ask the container to stay under that limit.
It enforces it.
It configures a Linux C group that acts as a hard physical boundary. If the application has a memory leak and tries to consume 501 megabytes, the kernel's out-of-memory killer instantly terminates the process.
Boom.
Dead. The kubelet enforces the physical reality of the scheduler's mathematical decisions.
And then namespaces provide the isolation. Like a Linux namespace ensures that the code running inside the container thinks it is the only software running on the entire machine.
Right, it can't see the other containers.
It has its own process ID tree, its own mount points, its own network stack. So the kubelet is orchestrating all of this kernel-level partitioning. But wait.
What is it?
The source text lists the container runtime as a completely separate component. It specifically points to tools like Containered.
It does.
Why do we need a separate runtime if the kubelet is doing all this kernel-level configuration with T groups and namespaces?
This raises an important question about the history and architecture of Kubernetes. Kubernetes is an orchestrator, right? It manages life cycles.
Okay.
But it doesn't actually unpack the file system layers of your Docker image. It doesn't actually make the final clone system call to the Linux kernel to start the process.
It outsources it.
That is outsourced to the Container Runtime Interface, or CRI.
So the kubelet is basically the architect drawing the blueprints, but Containered is the construction worker actually pouring the concrete.
Precisely. The kubelet uses the CRI gRPC framework to talk to Containered data. It says, here are the exact KEO groups and namespaces I need. Here's the URL for the image registry. Please pull the image, unpack the layers, and run the binary.
And Container does the heavy lifting.
Container then utilizes a lower-level tool, usually Runc, to actually interface with the kernel and spawn the process.
So why decouple it like that?
By decoupling the kubelet from the runtime, Kubernetes ensures you aren't locked into a single container technology.
Oh, that makes sense.
You can use Containered, you can use CRIO, or even highly secure sandboxed runtimes like gvisor, all without changing a single line of core Kubernetes code.
That modularity is genius. Okay, so we have the kubelet managing the node's resources and Containered actually running the binaries. But there is a third piece of the puzzle on the node.
The kube proxy.
The kube proxy. The text calls it a network proxy that runs on each node. Now, I want to challenge the necessity of this. If every pod gets its own IP address, why do we need a proxy?
That's a fair question.
Like, why can't my web server pod just talk directly to my database pod using its IP address?
Well, you can, technically. But pods are entirely ephemeral.
Right, they die all the time.
They are born, they die, they get rescheduled constantly. Every time a database pod dies and is recreated by the controller manager, it gets a completely new, unpredictable IP address.
Oh, I see. So if your web server hardcodes the IP address of the database pod, the application will break the second that database pod is restarted.
Right. It's like trying to mail a letter to someone who moves to a new house every 5 minutes.
You never find them. You need a permanent address.
And in Kubernetes, we call that a service.
A service, okay.
Exactly. A service provides a stable virtual IP address, a cluster IP. It never changes.
But that IP address doesn't actually exist on any physical network interface card, does it?
No, it's completely fake. It's a virtual construct.
Right.
And this is where kubeproxy works its magic. kubeproxy runs on every single node and acts as this dynamic, kernel-level switchboard operator.
Watching the API server again?
Yes, it constantly watches the Kube API server for updates to services and pod endpoints.
And how does it actually route the traffic? I've heard it relies heavily on Linux iptables.
Historically, yes. Kube proxy would write massive lists of iptables rules. When your web server tried to send a packet to that fake cluster IP, the Linux kernel would intercept it.
And then rewrite it.
Right. The iptables rule would use destination network address translation, or DNAT, to instantly rewrite the destination IP from the fake service address to the actual current living IP address of the database pod.
But I've read that as clusters scale to like thousands of services, iptables becomes a massive performance bottleneck because it evaluates rules sequentially, right?
It is a linear search, yes.
So if you have 10,000 rules, a packet might have to be checked against 9,999 rules before it finds a match.
Which is terribly slow. And that is why modern Kubernetes networking relies on IPVS IP virtual server.
IPVS, how is that different?
It's a transport layer load balancing mechanism inside the Linux kernel that uses highly optimized hash tables.
Hash tables. Oh, so it's not linear.
Exactly. Instead of an ON linear search, IPVS provides an O1 instantaneous lookup.
That is way better.
So much better. Kube proxy configures these IPVS hash tables. So whether you have 10 services or 10,000, Kube proxy ensures the packet is instantly and flawlessly routed to the correct endpoint.
It is an absolute masterclass in network engineering.
It really is.
This is staggering when you put it all together. We have the control plane acting as the brain, dispatching and monitoring. We have the kubelet partitioning the kernel, contained executing the binaries, and Kube proxy manipulating core network routing tables in real time.
It's an incredibly complex machine.
Which brings us to the most daunting question. How do you actually build this from scratch?
The installation.
Right. If you are sitting in an empty data center with raw, unconfigured Linux servers, how do you synthesize this entire organism?
That is the crux of cluster administration, and it moves us directly into the installation sequence. In the early days, you had to manually generate dozens of cryptographic certificates.
It's awful.
Oh, you had to write complex system service files, manually bootstrap the etcd database.
Yeah.
It was an agonizing, error-prone process, famously documented as Kubernetes the hard way.
The hard way, right. But today, our source document points us to a specialized bootstrapping tool, KubeADM.
Yes, KubeADM changes everything.
And the sequence in the document is very specific. It lists prerequisites, then install container runtime, then install KubeADM, kubelet, and kubectl. Only then do you initialize the control plane and finally join worker nodes.
You start at the absolute bottom. Prerequisites.
Okay, the documentation mentions that before you even download a single Kubernetes binary, you have to configure the underlying Linux operating system.
Yes.
And the most notorious prerequisite is that you absolutely must disable swap memory. Why is Kubernetes so aggressively opposed to swap memory?
Because swap memory fundamentally destroys the kubelet's ability to provide quality of service guarantees. We talked about how the kubelet uses key groups to enforce strict memory limits, right?
Exactly. If a pod exceeds its 500 megabyte limit, it gets killed.
But if swap memory is enabled, the Linux kernel doesn't kill the process. When physical RAM fills up, the kernel quietly takes the memory pages belonging to that container and writes them to the physical hard drive.
The swap space.
Yes. And hard drives are orders of magnitude slower than RAM. Suddenly, your high-performance database pod is running 1,000 times slower because its memory is paging to disk.
And the kubelet doesn't know.
The kubelet has no idea this is happening. The scheduler has no idea. The predictability of the entire cluster is compromised.
So it's basically lying to the orchestrator.
Exactly. So KubeADM enforces a hard rule. Disable swap, or the installation will fail immediately.
That makes perfect sense. You can't guarantee performance if the kernel is secretly offloading memory to spinning Rust.
Right. And there are also network prerequisites.
Yeah, enabling IPv4 forwarding and loading the Burnett filter kernel module. That allows the kubeproxy we just talked about to actually intercept bridge network traffic and apply its IPVS rules.
Crucial steps.
Okay, so the OS is prepped. The next step is installing the container runtime, specifically containered. We install the worker before we install the brain.
Yes, and this is where the elegance of modern Kubernetes architecture truly shines. We established earlier that Kubernetes manages containers.
Right.
But in a modern KubeADM deployment, the control plane components themselves, the Kube API server, the scheduler, the controller manager, and even etcd, they do not run as traditional system-level services.
Wait, let me make sure I'm following this. The brain that orchestrates containers is itself made out of containers.
Well,
how does that even boot up? It's a total chicken and egg problem. If there is no Kube API server running to tell the kubelet to start a pod, how do the API server pods start in the first place?
This is where a mechanism called static pods comes into play.
Static pods, okay.
Normally, the kubelet gets its instructions from the Kube API server, but the kubelet also has a secondary local method of receiving instructions.
That's a backdoor.
You can point the kubelet to a specific directory on the local hard drive, usually a Kubernetes manifests.
Okay.
The kubelet continuously watches this local folder. If you drop a pod specification file in there, the kubelet bypasses the API server entirely and just tells container to run it.
Wow. So we install container first, then we install kubectdm, the kubelet, and kubectl. We start the kubelet service.
Right.
So at this exact moment, the kubelet is running, container is running, but the cluster does not exist. There is no API server.
No.
The kubelet is just sitting there staring at an empty Kubernetes manifests folder, waiting.
Exactly. And that is when you execute the magic command, kubectdm.
Kubectdm.
When you run this command on your first control plane node, an incredibly complex choreography begins. First, kubectdm runs pre-flight checks to ensure swap is off and ports are open.
Right.
Then, it moves into certificate generation. It essentially acts as its own certificate authority, generating all the cryptographic keys required for mutual TLS authentication.
We will dive deep into those certificates later, but let's stick to the bootstrapping sequence for now. So kubectdm creates the keys. What happens next?
Next, kubectdm generates the kubeconfig files, the configuration files that tell the components how to securely talk to each other.
Okay.
And then, the critical moment. kubectdm generates the YAML specification files for the kube API server, etcd, the scheduler, and the controller manager.
The manifests.
Yes, and it drops those files directly into that Kubernetes manifest directory.
And the kubelet, which has been blindly staring at that directory, suddenly sees the files.
Yes. The kubelet instantly reads the manifest, talks to container count, and starts spinning up the core components.
Oh, that's amazing.
Within seconds, etcd forms its single node cluster, the Kube API server exposes its secure endpoint, and the scheduler and controller manager begin their watch loops.
The brain wakes itself up.
The cluster is officially alive.
That is legitimately brilliant engineering. It bootstrapes itself, and when the kubectdm init process finishes, it doesn't just say done, right? It prints out a very specific output.
It gives you a kubectdm join command containing a cryptographic token.
Because right now, you only have a brain, you have the control plane running on one node, but you have zero capacity to run actual applicational workloads. You need to hire the workers.
Exactly.
So you take that kubectdm join command, you log into a brand new raw Linux server or a worker node where you have already prepped the OS and installed container in the kubelet. You paste that command and hit enter.
Right.
Walk me through the mechanical reality of the join process. How does this raw server securely become part of the cluster?
It utilizes a process called TLS bootstrapping. When you run kubectdm join, the local kubelet takes that cryptographic token and reaches out over the network to the Kube API server.
Okay, presenting the token.
The token proves that this node is authorized by the administrator. The Kube API server verifies the token and then dynamically generates a unique client certificate specifically for that new kubelet.
So it mints a new badge for it.
It does. The API server sends the certificate back, the kubelet installs it, and securely registers itself. The API server updates etcd, the scheduler sees a massive influx of new CPU and memory capacity, and your worker node is ready to receive pods.
You repeat that join process for 10, 50, or 1,000 worker nodes, and you have a massive enterprise-grade compute fabric.
You've built the beast.
But he's built the beast. But here is the terrifying reality of infrastructure. Software rots.
Always.
Vulnerabilities are discovered. The community releases a new version of Kubernetes every few months.
And you have to keep up.
Once this massive, highly complex cluster is running production workloads like credit card processing, healthcare records, live video streaming, you eventually have to upgrade it.
Yes.
And you have to do it without dropping a single packet.
Maintaining a distributed system is arguably much harder than building it in the first place. You are essentially changing the engine of an airplane while it is flying over the Atlantic.
That sounds incredibly stressful.
It can be. Our sources outline the strict protocol for maintenance and safety, specifically focusing on the upgrade sequence and etcd restores. Let's start with upgrades.
Okay.
The documentation specifies a rigid two-phase process. Upgrade control plane, then upgrade worker nodes.
See, I want to challenge this. If I have automated configuration management like Ansible or Terraform, why can't I just blast the new binaries to all the nodes, control plane, and workers alike, and restart everything simultaneously?
Oh, please don't do that.
Why this strict sequential separation?
If you attempt that, you will completely destroy your cluster due to API version skew.
API version skew, what is that?
The Kube API server is the brain, and the kubelets on the worker nodes are the body. The Kubernetes community enforces a strict backward compatibility policy.
Okay, so newer understands older.
Right. A newer Kube API server is designed to perfectly understand the requests and status updates from an older kubelet. But the reverse is not true.
Oh, older doesn't understand newer.
Exactly. If you accidentally upgrade a worker node's kubelet to version 1.30, while your Kube API server is still running version 1.29.
The kubelet tries to speak a language the API server doesn't know yet.
Yes. The kubelet might try to use a brand new API endpoint or a new field in a pod specification that the old API server has never heard of. The communication breaks down, the node goes offline.
So the sequence is a hard law of physics in Kubernetes. You absolutely must upgrade the headquarters first.
Always headquarters first.
You run kubeadm upgrade, apply on the control plane nodes. kubeadm carefully downloads the newer images for the API server etcd and the controllers. And it gracefully restarts those static pods one by one, ensuring quorum is never lost in etcd, and the load balancer always has at least one active API server.
Exactly. Once the entire control plane is updated and healthy on the new version, it is fully capable of managing the older worker nodes.
Because of backward compatibility.
Yes. Then, and only then, do you begin upgrading the worker nodes one by one. And this involves the critical process of draining.
Draining.
You don't just kill the kubelet. You run kubectl drain on the node. The control plane politely evicts all the running pods, forcing the replica sets to recreate them on other healthy nodes.
Ah, so the workloads just shuffle over to other servers.
Safely empty. Then you run kubectl upgrade node, restart the kubelet, and uncordon the node to let workloads back in. You roll through your entire fleet this way, ensuring zero downtime for the applications.
That's incredibly elegant. You know, the source material explicitly mentions a practice scenario, upgrading a cluster from version 1.29 to 1.30. It's very specific about those version numbers. It doesn't say upgrade from 1.25 to 1.3.
And that specificity highlights the incremental nature of cluster maintenance.
Yeah.
You cannot leapfrog minor versions.
You can't.
No. If you are running 1.28 and want to get to 1.30, you must perform a full cluster upgrade to 1.29 first, ensure everything is stable, and then perform a completely separate upgrade to 1.30.
Oh, wow. Why is it so strict?
This strict sequential path gives the internal data structures in etcd time to migrate, and it ensures that deprecated APIs are phased out safely according to the community's lifecycle policies.
Speaking of etcd, what happens if the upgrade fails catastrophically? Or worse, what if a rogue administrator accidentally deletes the entire production namespace?
It happens more often than you'd think.
Right. Upgrades protect against software decay, but they don't protect against human error or massive physical hardware failure. The text dedicates a specific section to etcd backup and restore. Under key concepts, it explicitly notes etcd cluster state storage, backup restore critical.
The word critical is honestly an understatement. As we established, etcd is the sole source of truth. Every deployment, every secret, every network policy, every RBAC rule is stored entirely within etcd.
It's all in there.
The worker nodes themselves are completely stateless. Yeah. If a worker node burns down, you just buy a new one and join it. But if you lose your etcd quorum and you have no backup, your cluster is gone.
Gone. Ceases to exist.
It ceases to exist. You are starting over from a blank slate.
I think of it like the master save file in a massively complex video game.
That's a great way to put it.
You can spend thousands of hours building your base, gathering resources, configuring your characters. If the game console melts down, the hardware is replaceable.
Yeah.
But if your save file gets corrupted, all that time is lost. etcd is the save file for your entire enterprise architecture.
And backing it up is surprisingly straightforward because it is just a database file at the end of the day.
Yep.
You use a command line tool called etc.
Oh, okay.
You authenticate directly against the etcd endpoints using those cryptographic certificates QADM generated, and you run the snapshot save command.
That's it?
That's it.
Yeah.
This safely pauses compaction and writes a single .db file containing the entire point-in-time state of your cluster.
And restoring it is just as powerful, right? If disaster strikes, you take that snapshot file, you spin up brand new raw servers, and you use etc. snapshot restore.
Yes, it populates a new directory with the exact database state.
You point a new Kube API server at it, and instantly the brain wakes up, looks at the database, and says, oh, I'm supposed to have 5,000 pods running across these specific namespaces.
And the actual state is 0.
Right. The controllers immediately start screaming that the actual state is 0, and the system frantically begins rebuilding your entire infrastructure without you lifting a finger.
It is the ultimate disaster recovery mechanism.
Right.
But as you mentioned earlier, the greatest threat to a system usually isn't hardware failure.
It's people.
It is human error or malicious intent. We've protected the state of the cluster with backups, but how do we prevent a junior developer from accidentally executing a command that requires us to use that backup in the first place?
Yeah, how do we lock them out of the dangerous stuff?
This requires a deep dive into Section 5, security and access.
Okay, so the sources outline 2 massive pillars of security, RBAC and certificates. Let's tackle RBAC first, role-based access control. This system determines what an authenticated user is actually allowed to do.
Right.
The document breaks this down into 2 very distinct scopes. We have role and role binding, which are namespace scoped, and we have cluster role and cluster binding, which are cluster scoped.
Correct.
I look at this and see a lot of overlapping terminology. What is the fundamental mechanical difference between a role and a binding?
Think of it as the difference between a job description and an employee contract.
Okay, job description versus contract.
A role is just a purely theoretical document. It contains a list of rules. It specifies the API groups, the resources like pods or deployments, and the verbs like get, list, watch, create, or delete.
So a role might say, whoever holds this can create and delete pods.
But the role itself doesn't apply to anyone yet. It's just a definition. A binding is the mechanism that takes that job description and attaches it to a specific subject, like a user, a group, or a service account. The binding is what actually activates the permissions.
Okay, so the role is the list of permissions, and the binding hands that list to a specific person. But the source places a massive emphasis on the difference between namespace scope and cluster scope. Why is this boundary so critical?
This raises an important question. How do you implement the principle of least privilege in a multi-tenant environment?
Because clusters are expensive, right? You share them.
Exactly. A Kubernetes cluster is incredibly expensive to run. You don't build a separate cluster for every single development team. You have one massive cluster, and you logically partition it using namespaces.
So you might have a finance team namespace and a marketing team namespace.
Right.
So namespaces are essentially secure, isolated rooms inside the corporate headquarters.
Exactly. A standard role and role binding are locked entirely inside one specific room. If you give a developer a role binding in the finance team namespace, they have immense power, but only within those 4 walls.
They can delete every pod in the finance namespace.
But they cannot even run a simple get pods command to see what is happening over in the marketing namespace. They are cryptographically confined.
And a cluster role breaks those boundaries. It is cluster scoped.
It's the master key to the entire facility.
The master key. Wow.
If you assign a user a cluster role binding mapped to the built-in cluster admin cluster role, they bypass all namespace restrictions. They can delete underlying physical nodes. They can alter the core networking policies. They can destroy the entire system.
So connecting this back to you, the listener managing a real environment, you must be surgically precise with your bindings. You use kubectl to interrogate these rules constantly.
You really have to.
The practice question in the text asks, how do you check if a user can perform an action? You use commands like kubectl auth, delete pods, namespace finances Jane to simulate and verify exactly who holds the room keys versus who holds the dangerous master keys.
But here is the critical flaw in any RBAC system. RBAC is utterly useless if you cannot definitively mathematically prove the identity of the person asking for access.
Because anyone could just claim to be Jane.
Exactly. If I walk up to the Kube API server and say, "Hi, I'm the cluster admin, let me in," the API server doesn't just take my word for it. It demands cryptographic proof.
And that is where the final foundational piece of cluster architecture comes into play, certificates.
Yeah.
The source explicitly calls out certificates under key concepts, noting they provide TLS for secure communication. And it lists a very specific set of file paths on the Linux file system.
The PKI directory.
Yeah, we've got the CA, the certificate authority at Kubernetes, Kika.crt. We've got the API server cert, the etcd server cert, all living in these deeply buried peaky directories. I know kubeadm generated all these during the init phase, but mechanically, how do these files secure the cluster? Why do we need so many different certificates?
Because Kubernetes operates on a zero-trust architecture. We talked earlier about how the kuAPI server, the kubelet, and etcd are constantly communicating over the network.
Right.
Networks are fundamentally insecure environments. Packets can be intercepted, read, or modified by malicious actors. Traffic can be spoofed.
So you can't trust the network.
None of the components in a Kubernetes cluster inherently trust each other just because they're on the same network. They utilize mutual TLS, MTLS, to establish mathematically proven trust.
Mutual TLS. So it's not just like my web browser trusting my bank's website. The bank's website also has to verify my identity.
Exactly. Let's look at the communication between the kubeAPI server and etcd. When the API server tries to open a connection to etcd to save some data, etcd stops it.
It blocks it.
It pauses the connection. etcd presents its own server certificate, the acceptdserver.crd file mentioned in the text, to prove its identity to the API server. But then etcd demands to see the API server's client certificate.
So the API server has to show its badge.
Yes, the API server presents appserver-etcd-client.crt. But etcd doesn't just look at the badge and say, OK. It takes that client certificate and mathematically verifies the cryptographic signature against the root certificate authority-the CA.crt.
Ah, it checks it against the central authority.
Because etcd has a copy of the CA and it knows the CA signed the API server's badge, it can definitively prove that this connection is genuinely coming from the authorized API server and not a hacker trying to inject malicious data into the teeth store.
And once that mutual cryptographic handshake is complete, they negotiate a symmetric session key, and all the traffic flowing between them is heavily encrypted.
Exactly. Anyone wiretapping the network just sees scrambled garbage.
Yeah.
Every single interaction. The kubelet talking to the API server talking to the kubelet, the controller manager talking to the API server, is secured by its own uniquely generated TLS certificate.
It is an incredibly dense web of cryptographic trust. And the absolute brilliance of the kubeadm tool is that it handles this entire public key infrastructure automatically.
Oh, it saves so much time.
If you had to manually generate OpenSSL certificate signing requests, sign them with a local CA, and distribute them to the correct Kubernetes folders on every single node, a cluster installation would literally take days.
And one typo ruins the whole thing.
Right. But kubeadm does it in seconds, establishing an impenetrable zero-trust baseline right out of the box.
It's remarkable.
So what does this all mean for you? Let's take a step back and look at the sheer scale of the architecture we have deconstructed today. We started with the brain, the control plane. We explored the stateless, horizontally scaled kubeAPI server.
The receptionist.
We dissected how etcd uses the wrapped consensus algorithm to prevent split-brain scenarios and maintain a quorum-backed vault of truth. We looked at how the kube scheduler mathematically filters and scores nodes to dispatch workloads, and how the kube controller manager utilizes relentless edge-triggered control loops to force the actual state to match the desired state.
And we connected that abstract brain to the physical reality of the node components. We saw how the kubelet acts as the autonomous foreman, utilizing Linux C groups and namespaces to carve out physical boundaries in the kernel.
Right.
We clarified how the kubelet delegates the actual execution of binaries to the container runtime interface and tools like ContainerTube. And we broke down how kubeproxy acts as a dynamic switchboard, manipulating IPVS hash tables to route packets to ephemeral pod IP addresses.
We took all of those distinct, highly complex components and built the entire organism from scratch using kubeadm. We navigated the strict prerequisites, acknowledging why swap memory destroys QoS guarantees.
We walked through the kubeadm internet bootstrapping sequence, watching the system spawn its own brain using static pods in the Kubernetes manifest directory.
We joined worker nodes using TLS bootstrap tokens. We learned how to maintain the beast through strict sequential version upgrades to avoid API version skew, and how to survive catastrophic failure by snapshotting the etcd database.
Finally, we locked the doors, dissecting the precise boundaries of namespace-scoped RBAC roles and the zero-trust mutual TLS cryptography protecting the network layer.
It is, without a doubt, one of the most sophisticated feats of distributed software engineering ever created. We have spent an hour breaking down the mechanical reality of how these components interact, how they fail, and how they secure themselves.
But I want to leave you, the listener, with a final provocative thought that pushes beyond the boundaries of this current architecture.
Oh, I'm ready. Where are we going?
Everything we discussed today, the control loops, the scheduling algorithms, the TLS bootstrapping, is currently designed and maintained by humans.
We write the YAML.
We write the declarative YAML files. We trigger the kubeatum upgrade commands. We define the RBAC roles. But the foundational architecture of Kubernetes is entirely built around the concept of self-observation and self-correction.
It already heals itself.
The controllers are already continuously evaluating the state of the system and making autonomous decisions to heal it. As we integrate advanced machine learning models deeper into infrastructure operations, consider the inevitable evolution of this control plane.
Okay, I see where you're going with this.
How close are we to a paradigm where the cluster no longer just manages application pods, but actually begins to observe its own architectural bottlenecks?
Oh, wow.
A cluster that analyzes its own network traffic, dynamically rewrites its own IPVS routing algorithms, preemptively scales its own etcd quorum before a predicted hardware failure, and redesigns its own RBAC security policies based on behavioral anomaly detection, all without a single human administrator ever writing a line of YAML. The mechanical foundation for a self-evolving, autonomous infrastructure organism is already fully deployed. We are just waiting for the brain to wake up.
A self-analyzing, self-rewriting infrastructure? The thermostat's learning to rebuild the furnace on the fly? That is a terrifying and brilliant vision of the future, and it perfectly underscores why mastering this foundational architecture is so critical. Well, that is all the time we have for today's incredibly deep dive into the complex, autonomous, and mathematically beautiful machinery of cluster architecture. Thank you so much for joining us, for unpacking the mechanisms behind the magic. Keep exploring, keep building, and we will catch you on the next deep dive.
Thank you for listening. Keep questioning the systems you built. Goodbye.